Okay, in this video we're going to talk a little bit about exponential decay. Before we do, let's kind of look at what exponential growth functions look like and compare it to exponential decay so you know what you're looking for when you see these things. So in the last section we saw that if y equals a times b to the power x, this would be exponential growth. Let's start off by writing that this would be exponential growth if the a value is greater than 0 and the b value is greater than 1. If that happens, it's going to be exponential growth. And just to make a sketch of what's going on here, if you were to actually graph this, you start off with like a small amount and it grows, goes up and away, and it looks something like that. That's growth. Now on the other hand, decay, if we did decay, it's similar. You're still going to have y equals a times b to the power x, so everything's identical so far. However, the a value, although it's still going to be greater than 0, so far again everything stays the same, the b value has to be between 0 and 1. So it's some fraction or some decimal in between 0 and 1, and that makes it a decay model. So what happens here, if you were to graph a decay model, is you might start off very, very high, and then this thing will come down low and approach that x-axis or your asymptote as you go to the right. So it's like almost the reverse of what exponential growth is. Now, on the other hand, you're going to have neither if the following occurs. So it's going to be neither, meaning neither growth or decay, if you have y equals a times b to the x, where a is less than 0. Right then and there, if you see a less than 0, you know it's neither growth or decay. Okay, it's got to have, if it's going to be growth or decay, your a value's got to be positive to begin with. So a couple of questions I might give you on a quiz or test is just to look at some functions and tell me if it's exponential growth, decay, or neither. And essentially, all you need to determine for all of these is, okay, what's the a value and what's the b value? If you know that, and you've studied and you know what those parameters are from above, you'll be okay. In this case, my a value is 1/3, and all that's important with the a value is that it's positive, right? And 1/3 is bigger than 0, so we are in the hunt for either growth or decay. Now the base is 3/2, which is 1.5. That's a number that's bigger than 1. So that looks like it's falling in that growth category. So let's go ahead and identify this one as exponential growth. Let's look at part B. In part B, this is kind of interesting. The a value, you might notice right away, is just 1/3, which once again is bigger than 0. So we're in the hunt for growth or decay. And if you just kind of took this at face value, you might think that your base is 2. But it's actually not. If you take a look, you got a negative exponent there, and that doesn't fit either form. If you take a look at all the forms that we have up above, it's just x as an exponent. It's not a negative exponent. So if we had to rewrite this with a positive x, we would do the following. Think of it this way. It's 1/3 and then 2 raised to the negative 1 times x. Would you agree that's the same as just 1/3 times 2 to the negative x power? I hope so, because it is. You would just multiply the x and the negative 1 to make negative x. But I can now apply that negative 1 power to the 2, making this 1/3 times 1/2, right, if you move the 2 downstairs, to the positive x power. Now I still have the same a value of 1/3, but my b value, you can see, is not 2, it's actually 1/2. And a lot of students get tricked on that because of the negative exponent, and you have to apply the negative to the base and bring the base down into the denominator. Okay, so now our base is actually a half, which does put it between 0 and 1, and that makes it a decay model. This makes it a decay model. Let's do one more together. Here I have an A value of 4 and a B value of 5 over 8, which I think is like 0.625. It's clearly between 0 and 1. I don't have that negative exponent trick to worry about here because it's just the positive x. And since this is a number between 0 and 1, and my A value is positive, this is another decay model. Now, what I want to do next is graph decay models. They're very similar to graphing growth models. If you recall, the graph of an exponential function, a times b to the x, will always pass through the point 0, comma a, and it will always have, if there's no shifting, right, it's always going to have the x-axis as an asymptote. The domain is going to be all real, and the range is going to be all y values that are greater than 0 if the a value is positive, and y values that are less than 0 if the a value is negative. Really, everything that I just said is the same thing from section 8.1. Nothing has changed. However, the look of the graph will be a little different. We've never graphed ones quite like this. By the way, if you look at A, let's just think about if this is growth, decay, or neither. Our A value is -2. Hopefully you recall this, if your A value is negative, if it's less than 0, this is actually neither growth or decay. And actually, because our base is 1/3, which is between 0 and 1, right? This is like a decay model, which if we had an image in our head of what decay looks like, it's like this. However, whenever your A value is negative, it's going to be a reflection of that graph over the x-axis. So if you were to go ahead and like take a reflection over the x-axis and flip that over, you'd get something like that. So I kind of know already that this graph is going to look something like the guy here in orange. Now, it helps that I have experience, right? You don't maybe know that yet, but you soon will. Let's graph this. I'm going to plot a few points. If we plug in 0, we'd get 1/3 to the 0, which is 1, and we would get an output of -2. So I'm going to plot 0, -2 right there. If I plug in 1, then I'd have, let me just maybe write it over here if it's okay. I'm going to erase some of this stuff that I had done before. So if we had plugged in 1 again, this would be -2 times just 1/3, which is -2/3. So if I plug in 1, -2/3 is like -0.7 if we had to round to one decimal place. Now, rather than plug in 2, I'm going to plug in -1. I kind of like plugging in 0, -1, and +1 for these guys, as you'll soon see why. If I plug in -1, I'm going to have -2 times 1/3 to the -1 power. Now you know if you take 1/3 to the -1, you'd have to flip that base because, let me maybe really analyze this so everybody's clear. If you have -2 and we distribute that -1 power to the 1, it's going to be 1 to the -1 and 3 to the -1, which means you have to flip them. So it's going to be -2 to the 3 over 1 power, which is really just 3. You'd get out -6. So that's kind of a nicer coordinate to plot than if we were to plug in 2. I think if we plugged in 2, we'd get some really small decimals. So here I can plot a nice -1/6. Now keep in mind the x-axis is our asymptote, and we start low and we're going to come on up and flatten out and approach the x-axis as we go to the right, and it kind of falls down as we go to the left. Your domain is going to be all reals, and our range is going to be all y values less than 0, and that's because the graph is underneath the x-axis, and that's due to that negative in front of the 2, right? It's a -2 for our leading coefficient there. Let's look at another graph. Here, ooh, this one's got some shifting. So this is kind of like what we had finished the last section with. If I were going to graph this and make my life easy, I'm going to ignore all that stuff right there first and graph only my parent functions. So this is our parent. Our parent is y equals 5 times 1/8 to the x power. Let's plug in a couple values here. If you plug in 0, you're going to get 1/8 to the 0, which is 1, and 1 times 5 is 5. So you can plot 0, 5. If you plug in 1, you're just going to have 1/8 to the first, which is an eighth, times 5 is 5/8. And then instead of plugging in 2, I'm going to plug in -1. And if you plug in -1, remember, that's going to be like 5 times. We'd have to flip the 8 over 1, or excuse me, the 1 over 8 to be 8 over 1 if we had applied the negative exponent. And that would actually give us, what, 40? Maybe that wasn't the best after all. That's way up high, right? Let's try 2 after all. If we do 2, it's going to be 5 times 1 over 64 if you square 1/8. And that's a really small value. That's going to be 5 over 64. That's so small, it's pretty close to 0 as far as graphing is concerned. So if we plot these points, we have 0, 5, right? So 0, 5 is right here. When we plugged in 1, we got 5/8, which is just a little bit more than half, so ballpark right there. When we plugged in 2, it was even closer to 0. So you can see these points kind of fall down pretty quickly. And by the way, this is a decay model. Our A value is 5, bigger than 0, and our base is a number that's between 0 and 1. It's 1/8, right? So it's definitely decay, and we can see that as these points are falling from going left to right. Now, what I need to now do is shift. Remember, this is not our final answer. Our h value in this problem is really a -1, so that means 1 to the left. And our k value is really -2, which means 2 down. So we're going to translate or move these points all 1 to the left and 2 down. Let's start with this guy. 1 to the left and 2 down. Right there is my new point. If I go this guy, 1 to the left and 2 down, it's going to be about right there. This guy, 1 to the left and 2 down is right there. Now remember, when we go any vertical shifting on these, the asymptote also gets shifted. So we went 2 down. The asymptote that was the x-axis now got shifted down 2 as well to y equals -2. That's our asymptote. So if I were to clean this up, really the graph that we want to have for our final graph is going to start up really high, and it's going to come down on a smooth curve. Now this one bends so quickly that it's going to almost look like a sharp edge. It's hard to not make it look like a sharp edge, but we get some kind of graph like that where a decay is going from left to right. Let's talk about the domain real quick. The domain would be all real, and the range would be all y values that are strictly greater than that asymptote at -2, because we have all y values above it. The last examples I'm going to show you are decay models, and these are actually very similar to exponential growth models. If you recall, when we had exponential growth, it was y equals a and then 1 plus that percent change r to the t power. Now, when a real-life quantity decreases, and the key word here is it decreases by a fixed percent each year or other time period, the amount y of the quantity after t years is almost the same. You still start with your initial amount a, and instead of 1 plus r, we're taking away that percent from 1 to make it decrease. 1 minus r to the t power. Now that should make sense, because remember, for decay, remember this base is supposed to be between 0 and 1. And so by subtracting that rate, you're guaranteeing that your base will be a number that's between 0 and 1, thus making it decay. So remember, a is the initial amount. I'm just going to write initial amount like that. R is the percent decrease as a decimal. Of course, right? We never put in just straight percents into our formulas. And the quantity 1 minus r is called the decay factor. Whereas, remember in growth, 1 plus r was called the growth factor. This example that I'm going to do for you actually has to do with a car that I bought when I first started teaching that was worth $37,000 new. It was determined that the car's value decreased by 4% a year, and we want to find out what is the car worth after 5 years. My hint to you is let's first write a model for the car's worth after t years. Now, just to kind of back up, a lot of students don't realize that when you purchase a car, as soon as you make that final signature and you've paid for that car, even though you may not even have driven it off the lot, and everything is paid for, that car's value just decreased. Almost all cars decrease in value over time. There's only a few cars that actually increase in value. It's one of the things I would like to convince my wife of. Let me buy a nice car that would actually be one of those things that increases in value over time, and that would be a nice investment. But we don't have anywhere to put it right now. So maybe one day that'll happen. Anyway, we're going to use the formula y equals a, then 1 minus r to the t power. Now, remember, the key word to know that we're going to do 1 minus r is that it's decreasing in value. So we know the initial amount is $37,000, so I'm going to put in 37,000 here, and it's going to be 1 minus the percent. Now r as a decimal, remember r is 4%, right? But that's not a decimal. As a decimal, that'd be 0.04. So we're going to use 0.04 for r. So I'm going to do 1 minus 0.04 to the t power. This is our formula. And actually, let's write it one more step. So it doesn't look quite as ugly. 1 minus 0.04 is the same as 0.96. Now there you go. Isn't that number, that base, 0.96, is between 0 and 1, and that's going to guarantee that this is decaying over time. We're getting smaller over time. To answer the question, our t value is after 5 years. How much is the car worth, right? So we're just going to substitute in 5 and get 37,000 times 0.96 raised to the 5th power. And if you put that into your calculators, and you can go ahead and do that with me now, 37,000 and then 0.96, raise that to the 5th, to the nearest penny, the car's value has gone down to only $30,168.79 if we were going to be that picky about going to the nearest penny. So the car's value has decreased roughly, $7,000. What I'd like you guys to try now for your self-quiz is a couple of graphs, one that doesn't have any shifting, and then another, part B, which does have shifting. Oops. And the last question, C, is one of those exponential decay models. So good luck, and we'll see you tomorrow.